These can be priced using the Black-Scholes formula, and we saw this earlier. We applied Black-Scholes formulas for exchange options. And in both cases, these are the prepaid forward values. This is the prepaid forward value of S from 0 to time t, and this is the prepaid forward value at time t of the risky asset K. Namely, in order to do that, what one does is discount the initial price by the continuous dividend flow, and that's the prepaid forward price of 1 unit of S, and this is the prepaid forward price. So hopefully this looks familiar from the earlier module that expressed the Black-Scholes formula in terms of prepaid forward prices, and that's exactly what this is. However, in doing this, we need an adjustment to sigma. All the rest of the formula here looks familiar from that earlier chapter, but now we need to rethink what is sigma. And sigma is, in fact, the variance of a log ratio between S and K. That what one needs to do is to calculate, and how would we do that? Basic idea is if we looked at, let's move ahead and do that calculation, and we'll come back. So if we want the variance of the log of S over K, we're looking for the variance of a return on the ratio S over K. So what we're saying is that we first of all look at the ratio at time t plus 1, and we divide that by the ratio at time t. And then we take the log. Right, it's the log ratio. So this is this is kt. So we're looking at the ratio of S divided by t. Now, how do we find in the continuous compounding? We have the model where st plus 1 is equal to st e to the r, and the volatility is the standard deviation of r. So we're trying to reproduce this model. How do we get the standard deviation of r? We calculate the standard deviation of the log of the ratios, st plus 1 to st. So I'm doing the same thing here, but what I'm looking at is instead of just one price, I'm looking at the ratio of prices. So I look at the ratio of prices at time t plus 1 and the ratio of prices at time t, and I take their log, and I want the standard deviation of that. Now, by virtue of logs, this is equal to the log of st plus 1 over st minus the log of kt plus 1 over kt. So the standard deviation that we're looking for sigma, which is the, well, let's say, let's work with variance, because then we don't need a square root. The variance we're looking for is the variance of these multiple log ratios, this term here. And by this expression, it's equal to the variance of the log ratio of S and log ratio of K. So we know the variance of a sum or the variance of a difference reflects the individual variances and a correlation. And then we get that this is the variance of S plus the variance of K, and then we have minus 2 row standard deviations times, and that's what we have. And that's the formula we see in the book just by using these. So that the variance that's needed in this particular option is in fact given by the variance of the ratio of prices, which we calculate using the variance of the returns of each sequence separately along with the correlation of those returns. So as some examples, exchange options we can think of as generalizing Black-Scholes. The earlier generalization we looked at didn't contemplate that we had two risky assets. It contemplated we had one risky asset which we were exchanging for a non-risky asset, and we were looking at prepaid forward prices. Here we're generalizing it further. However, if we let the S delta be the stock dividend and the K delta be R, then K becomes a T-bill. And this is the a plain vanilla Black-Scholes call. If we interchange the roles of delta S and delta K, we can now reproduce a Black-Scholes put, namely by letting delta S be R, the cash yield, makes S in effect a T-bill, although mislabeled, and if we let delta K be a true delta and make it a risky stock, then there's no volatility for S because it's now a T-bill, and this becomes a Black-Scholes